Thank you very much. A pleasure to be back here talking to Chester. For the last half hour or so, we've been watching cosmic rays coming through the room using this cloud chamber. Every once in a while, we see a flash, a little bit like a very brief contrail left by an aircraft. Every once in a while, you see a little trail of alcohol droplets left in the cloud chamber. We'll be coming back to this because I can't waffle any further. There's a couple that come through, okay. I can't waffle forever, and like buses, you wait for ages and then 3 come along at once. So let me go back to the PowerPoint. I'll be swapping backwards and forwards between PowerPoint to give you basically the theory and jumping back to the demonstrations on the front table here. So yes, this is cosmic rays. We're asking what they are and where they come from. So after a little bit of an introduction, I'll give some background before launching headlong into cosmic rays and cosmic radiation. I'll be covering a little bit of background on what do we mean by radiation, what we mean by terrestrial radiation from here on Earth, before we launch into how does that differ from radiation coming from the rest of the cosmos. I'll be saying a little bit about detectors. In other words, the detectors we've got here, a cloud chamber and a Geiger-Müller detector. And I'll be finishing by saying, well, okay, cosmic particles are raining down on the Earth, but where are they actually coming from? And then I'll finish with a very brief summary. So firstly, I need to say that yes, there are some radioactive samples sitting here on the front table. And yes, the Chester AS lawyers have insisted that I tell you that this is a radiation risk. There is only a radiation risk to me, not to you, and I will be putting the radioactive samples away, and so you're welcome to approach the bench and have a closer look at the cloud chamber when I've put the radioactive samples away towards the end of the demonstration. The radioactive samples are just natural rocks that can be dug out of the ground, but because they're radioactive, we have to make that statement. So I'll be using a couple of demos on the front bench here. One of them, the yellow box there on the left, commonly called a Geiger counter, and on the right, a little cloud chamber that I've made that allows us to see radiation. So let me start by just switching on the Geiger counter. Let me swing around. Oh, you can't see it anyway, so we'll come back to that in a second, but hopefully you can hear that. A click every few seconds. So what is it that's doing the clicking? Well, okay, that particular box is often called a Geiger counter. Physicists don't like that because it should be called a Geiger-Müller detector to recognize the inventors, but everybody calls them Geiger counters, so we're going to stick to just calling it a Geiger counter. It's something that clicks whenever a subatomic particle flies through the detector being this thing at the front there. So where do these subatomic particles come from? They're clicking away. We're sitting here in Chester. The radioactive samples are not close enough to actually activate the Geiger counter, and the radioactive samples are actually sitting in a metal box which shields them. So where are these clicks coming from? Well, maybe these clicks are recognizing the fact that a subatomic particle has gone through the Geiger counter, and maybe the subatomic particles were spat out of an atom that is floating around somewhere in this room. But it's also possible that the clicks you're listening to have their origins much further afield. Maybe the clicks signify the passage of a subatomic particle that might have started its journey in a supernova somewhere within our galaxy, or possibly within a galaxy far, far away. The bottom line is we can't tell from the click. The click just tells us something has been detected. It can't tell us the origin of those subatomic particles, which is one of the reasons it's taken a while to figure out what cosmic rays actually are. So let's have a demonstration of some background radiation. So radiation is around us all of the time. It's not something necessarily to be afraid of. We have to remember that planet Earth is radioactive. That's not because of what mankind has been doing to planet Earth. Planet Earth was made radioactive. It's been radioactive for the last 4.5 billion years because it was made out of some elements which are unstable and are radioactive. They change. So let me just explain what we mean. If you look at all of the elements in the periodic table, all 100 or so of them, Some of them are stable. Stable means, in the context of atomic physics or nuclear physics, stable means once an atom is made, that atom effectively is eternal. It lives forever. For the moment, let me just switch off the clicking. We'll come back to that in a moment. But a stable atom means once you've made an atom, it remains stable forever. But some of the atoms, some of the elements in the periodic table of elements are unstable, which means they decay. That doesn't mean they go moldy. That means that as far as a physicist is concerned, they change into another element. And in the process, the nucleus of the atom of that element changes, and it spits out something, usually a subatomic particle. So let's visualize what's actually going on by having a look at some uranium. So again, we're going to switch back to the video. So now we're looking at the Geiger counter, and I'm going to demonstrate, well, this is not the smallest piece of glass I could possibly have chosen. Here's a piece of glass with some uranium doped in it. If I bring it up to the Geiger counter, it is quite definitely radioactive. Why do people put uranium into glass? Well, it's not because you want to make it radioactive. It's because of its byproduct, and that is, if you were to illuminate it with UV light, it fluoresces. It fluoresces like mad, basically. And just for the demonstration of anybody watching this video rather than live here in the room, I've just demonstrated that uranium glass under UV light really does fluoresce quite madly. But that particular piece of glass is a little bit large to put into the cloud chamber. So far the cloud chamber has just been sitting there showing us cosmic rays. But now I'm going to demonstrate radioactivity by taking a tiny piece of a mineral with some uranium in it. If I can do that very carefully. Let me just convince you that it is actually radioactive. It is tiny, as you can see, it's barely a millimeter or two, but it is quite definitely radioactive. If we come back to the cloud chamber, what I'm now going to try and do is to put this sample inside the cloud chamber with the minimum disruption to the cloud chamber itself. Not sure I got away with that, but there we go. So I've just disrupted the cloud chamber by opening it up, which means the alcohol vapor inside might take a little bit to settle. We are generating alcohol at the top of the cloud chamber, which is, as you can see from the drizzle there, slowly raining down to the bottom of the cloud chamber. And hopefully, in a little while, if I keep waffling for long enough, we will see that this particular piece of uranium mineral is generating something which hopefully will produce tracks similar to the cosmic rays that we were seeing just a moment ago. How long I have to waffle is different every time I give this talk. Sometimes it only takes a few seconds. This time it seems to be taking just a little bit longer, but it's worth waiting because I'm sure they will come along in just a moment. Whilst we're waiting for them to show, let me remind you that a cloud chamber is something in which, instead of having clouds made in our atmosphere from water vapor, where the water condenses into clouds at the right height and the right temperature, and hence the passage of an aircraft might result in a contrail being left behind it, here, a cloud chamber is made with alcohol because it's easier to vaporize alcohol and then condense it than it is to vaporize water and then condense it. So this particular cloud chamber is made using alcohol, but it's the same idea. Alcohol is condensing into clouds, and just like an aircraft might leave a contrail behind it, here a radioactive particle that's spitting out subatomic particles should leave tracks in the cloud itself. I was looking away and somebody said yes, so let's have a look at what's going on. It should get a little bit better as time goes by. Let me grab my pointer just in case I need it. Okay, did everybody see that one coming off on the left-hand side? There will still be cosmic rays in the background because we're not stopping cosmic rays. But any track that seems to start or stop, there was a nice one, start or stop with the radioactive sample itself, it is fairly clear that those radioactive particles are coming from the rock. If we get a particle in the middle of nowhere that doesn't seem to be coming from the rock, that's probably just a cosmic ray in the background. But as the cloud chamber has now settled, you can now start to see that this little piece of rock is spitting out lots of something. We can't necessarily tell what it is directly, but the cloud chamber is telling us that this rock is spitting out something. And if we watch it for a few minutes, you might start to recognize that some of those tracks are relatively narrow and quite bright, and some of them look a bit broader and a little more ghostly. So in other words, it looks like this particular piece of rock is spitting out two types of subatomic particle. So even without knowing the physics, we can simply interpret what we're looking at from this rather visual way of telling that rocks are radioactive, or at least some rocks are radioactive. So let me jump back temporarily to the PowerPoint. I had absolute faith that the cloud chamber was going to work, but just in case it didn't, in good Blue Peter fashion, this is a bigger chunk of rock sitting in the same cloud chamber on my kitchen table, taken a while ago, and again you can see it is spitting out something. In this particular case, I took a video over a minute or two and then added up all of the frames together so that you have a better idea of what's going on. Again, I forgot to switch the sound off. Let's just kill the Geiger counter for the moment. So perhaps it's easier now to see by adding up all of the frames of the video. Some of these tracks are relatively thin and well defined, and some of these tracks are altogether more ghostly, rather broad and rather more ghostly, implying that we've got at least two types of thing coming out of these atoms in the rocks. So it's definitely emitting something, but what are they that are leaving tracks in the cloud chamber? Let's remind ourselves what atoms are. Atoms, okay, not a fantastic representation of what an atom is, but it will do. An atom is a positively charged nucleus and a whole load of negatively charged electrons buzzing around it. The nucleus is the only thing that determines whether an atom is radioactive or not. It's got nothing to do with the outer electrons. It is the nucleus of an atom that determines whether that atom is stable or whether that atom is unstable and is going to change into something else. Now, this is a rather busy slide, but this is just reminding us that if you've got a nucleus, this is a very big nucleus, like, I don't know, the nucleus of a uranium atom or something like that, not necessarily a lightweight part of the periodic table, a nucleus might conceivably spit out a lot of different things. In other words, it might spit out a proton. The number of protons in the nucleus determines what the atom actually is. And a nucleus might not be happy with the number of protons it's got and wants to spit one out. It also might want to spit out a neutron, a neutrally charged particle, because it's unhappy with the configuration that it's got. It also might decide to spit out more than one at a time. It might decide to spit out 2 protons and 2 neutrons, which is so common, it's called an alpha particle, or the nucleus of helium, if you prefer. It's a very stable structure, which is why 2 protons and 2 neutrons often fly around together. And it's also possible that a nucleus can spit out an electron, a beta particle, so called because when they were first discovered, they weren't sure what they are. We now know that beta particles are electrons. But they can occur as either the familiar electron, negatively charged, or a positively charged electron, or a positron. Another way of thinking of that is to say it's the antimatter equivalent of the electron. And finally, it's also possible for a nucleus to spit out a gamma ray. Gamma ray is a little different from all the others because a gamma ray is an electromagnetic wave, not a particle like an electron or a proton or a neutron. So we're not going to go through all of the physics of how that happens, but the sort of radiation that you're often familiar with at school, for instance, is that there are alpha and beta and gamma rays. And in this context, a ray is the same thing as a particle. Historically, they weren't sure when they first measured alpha rays or beta rays. They weren't sure what they were. Are they waves, as in the wave of light, or are they actually particles? So these days, we don't really care whether we talk about alpha particles or whether we talk about waves. We don't really talk about beta rays. We might talk about beta particles. It really doesn't matter. They're all the same thing. Alphas are A nucleus of a helium atom, an alpha particle, is 2 protons and 2 neutrons together. They're quite heavy, they don't travel very far, so for instance, alphas do not travel through the glass of a cloud chamber. Beta rays, or beta particles if you prefer, are effectively electrons, either positively or negatively charged. They're lightweight, they rattle around inside a cloud chamber, and they're more penetrating, so they can travel through thin bits of metal, they can travel through glass. Gamma is a little different because gamma is an electromagnetic wave. It's a very high energy version of light, if you like. And it's only charged particles that leave tracks in cloud chambers, so we only see alphas and betas out of this set of 3. But we will see, as we can see shortly, other particles in a cloud chamber. So if we bear that in mind when we go back to the, video again, what we're looking at here, now that we recognize what we're seeing, we can now say, yeah, this rock is definitely spitting out some electrons, the very narrow, very bright particles that we see here, and the rather more broad, rather more ghostly tracks that we can see there are alpha particles. Remember, we're not going to see any gammas coming from this. Even if it's spitting out gammas, gammas will not show in a cloud chamber. They'll make a click in a Geiger counter, but they don't they don't produce tracks in the cloud chamber. So I'm going to take that sample out because we want to come back to cosmic rays, which is what this talk is all about. So I'm going to give it a little time to settle by removing the sample, putting it back in its box, and taking it out of harm's way. Okay, we are done with that for the time being. Let's come back and remind ourselves that, yes, there's the old video I showed before, there's the tracks. So the thin ones are electrons and the fat ones are alpha particles, or alphas and betas, or electrons and alpha particles if you prefer. To make sense of something I'm going to say a little later, I need to tell you a little bit about radioactive isotopes. Isotopes are cousins of the same type of atom. So let's give you a particular example of that. Let's take carbon as an example. Carbon has 6 protons in the nucleus because that's the definition. The number of protons in the nucleus of an atom defines what type of atom it is. So if you've got an atom with 6 protons, by definition, we label that carbon. If it also has 6 neutrons, then because 6 protons plus 6 neutrons equals 12 in total, we call that isotope carbon-12. And the carbon in your body is mainly carbon-12. But you're also made of another isotope, a cousin of carbon-12, is carbon-14. That is similar with the same 6 protons, but now 8 neutrons. So 6 plus 8 equals 14. That particular isotope is called carbon-14. There's a little bit of carbon-14 in your body, and it is radioactive. So you are radioactive. Carbon-14, that's the radioactive isotope that is used in radiocarbon dating. If we want to know how old a tree was, how long it has been dead, we use the amount of carbon-14 compared to the amount of carbon-12. That ratio tells us how long it is since that particular tree or organic material was alive. So where does it come from in the first place? If it's radioactive, that means it's decaying and changing into something else. Well, it's not something I'm going to go into, but actually carbon-14 is the origins of carbon-14 are actually in cosmic rays. In other words, cosmic rays hit the atmosphere and make carbon-14. In terms of a little bit of carbon-14 in your body, but most of the radiation that you are carrying around with you is potassium. Potassium is basically the most abundant of the radioactive elements. Perhaps you don't think of potassium as being radioactive. Well, not all potassium is radioactive, but potassium has radioactive isotopes. In your body, at the moment, I would estimate that 4,000 atoms per second are decaying into something else. They're decaying into argon and spitting out some radiation. Now, if you think 4,000 atoms is a lot, that is tiny compared to the number of atoms in your body, which is way, 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 way bigger than that. So 4,000 per second is certainly not something to worry about. It's one of the largest contributions to background radiation, but it is not a problem. Thorium is more abundant than uranium, and uranium is more abundant than you think, or at least I would hazard a guess that uranium is more abundant than you think. You might think of uranium at the top end of the periodic table as being a very rare element. Well, actually, it isn't. If you look at it, at 3 parts per million, there's 500 times more uranium than there is gold in the Earth's crust. It's just economically easier to take the gold out of the Earth's crust than it is to mine the uranium. But there's huge amounts of uranium all over the Earth. In the Earth's core, these elements, the potassium, the thorium, and the uranium, are responsible for keeping the core of the Earth hot and keeping the core molten. It's nothing to do with heat from the sun. The Earth has a molten core because of the radioactive decay of elements spitting out subatomic particles, and the energy of those particles is keeping the core of the Earth molten. And if we have a molten metal core spinning, we have a dynamo, which means we have a magnetic field. So the Earth's magnetic field is a consequence of radioactive decay in the Earth's core. And in a rather interesting cycle of life, it's the magnetic field of the Earth that protects us to some extent from radiation from outside the Earth. So it's interesting that radiation is being used to protect us from radiation. An interesting cycle. And just as a little sort of amusing aside, let's say something about antimatter. One of the isotopes of potassium is called potassium-40, just like carbon-14 in your body, an isotope of carbon. Well, of all the potassium in your body, one of the isotopes is called potassium-40, and that emits beta plus radiation. Beta means a type of electron, but it's not the familiar electron which make up all of our atoms, which are negatively charged. This particular electron is positively charged, meaning it is an anti-electron, or if you like, the antimatter equivalent of an electron. It has the opposite electrical charge to our familiar electrons. So any food that's rich in potassium is emitting antimatter. So Brazil nuts, bananas are antimatter generators. This gave rise to the rather whimsical idea of, can we have a banana equivalent dose? Instead of talking about radiation doses using physical units like millisieverts and other things that people don't understand, can we actually equate small doses of radiation to, well, how does that relate to eating a banana? And so, for instance, if you say, well, that's eating one banana, that's the radiation dose you get from eating one banana, you can then ask the question, okay, cosmic rays are passing through us all the time. We've seen it earlier this evening. How much does everybody get during a day? If you work out the dose that you get from the radiation of cosmic rays, how does that equate to eating one banana? And the answer is cosmic rays during a day equates to a couple of hands of bananas. Slightly different if you fly a lot, because if you fly a lot, you're closer to the cosmos, and if you're closer to the cosmos, you receive more cosmic rays. We'll see that in a little while. And before I finish this particular section on radiation from the Earth, before we talk about radiation from the sky, let me say that radon is a radioactive gas. Not all radioactive materials on Earth are solids. A few of the ones I've got here are little rock samples, but there's one in particular that is formed in gas form. Radon is a radioactive gas that's formed from uranium. It's the radioactive decay of the small amounts of uranium that occur naturally in rocks, especially granite. Granite nearly always contains a bit of uranium. Uranium will ultimately decay into radon. Radon is a gas, and that will bubble out of the rocks. So any room, essentially anywhere in the world, could contain a little bit of radon. It depends on how much granite there is under your feet. And if we look at where most of the granite is, if we look at the type of ground that tends to produce radon, you can see that it tends to be where the granite is. In mountainous areas like Cambria or the southwest, for instance, Cornwall especially. Here in the sort of Merseyside-ish area in the northwest, it's the lowest value. In other words, there's not much radon generated around here. So if we were to take the cloud chamber down to Cornwall, we would see many more alphas, because it's alphas that are generated by radon gas. Here we will see some alphas generated in the cloud chamber, because there is a little bit of radon floating around in every cubic meter of every part of the UK. Okay, so I've tried to give you a little bit of background about what radiation is, how we measure it in the UK, or how we measure it here on the surface of the Earth. But now we need to get back to the main theme of this talk, which is cosmic rays. So where do things start? Well, the pioneers of studying radiation back in the late 1800s and early 1900s were these people. I'm sure you recognize the person in the middle, Marie Curie. You might conceivably recognize the person on the left, Henri Becquerel. Perhaps you don't recognize Victor Hess on the right-hand side. Becquerel discovered radioactivity, and then some years later, Marie Curie started synthesizing various radioactive elements like polonium and radium, for instance. Victor Hess, he comes into our story in just a short while. But back in those days, at the turn of the previous century, it was realized that there is background radiation around us. The particular way of measuring radiation at the time was a so-called gold leaf electroscope. If you take gold leaf and charge it up, two very thin, very lightweight leaves of gold. If you charge it up so they have the same charge, like charges repel, so if you charge it up, positive or negative, those two leaves will separate, indicating that a charge is present. And it's in a little bell jar just to stop drafts affecting the experiment. But it was noticed that whenever they charged up a gold leaf electroscope, it would discharge. In other words, the two leaves would collapse, indicating that charge has been added or charge has left the particular system that they were trying to charge up. It looked like there was background radiation adding to the charge or taking away charge from this system. So there appears to be background radiation according to the detectors of the time. But the big question in the late 1800s was, where is this background radiation coming from? If we know where it's coming from, then we have a chance of figuring out what it actually is. Is this background radiation coming from below our feet, i.e. the Earth, or is it coming from the sky? So in 1910, Theodore Wolff said, okay, I'll take an electroscope to the Eiffel Tower. I'll measure the radiation levels at the foot of the tower, and then I'll take this electroscope, this radiation detector, to the top of the Eiffel Tower and see if the readings tell me that the radiation has gone down, implying that the radiation is coming from the Earth. When this experiment was done, the radiation levels sort of changed, but not by enough to be absolutely sure what was going on. It wasn't consistent with the radiation coming only from the ground, so maybe it was coming from the ground and the sky. The jury was still out at this time. They weren't sure, for instance, whether the Eiffel Tower was radioactive. Not a silly thing to think about. The Eiffel Tower is made of iron. Iron is dug out of the ground. If the ground is radioactive, maybe the tower is radioactive. And at this point, it was already known that radon existed. And if radon exists, how do we know that the atmosphere isn't radioactive? In which case, can we expect to get a change of reading between the bottom of the Eiffel Tower and the top of the Eiffel Tower? This is where Hess comes in. Hess said, maybe the height of the Eiffel Tower is not enough. If we want to resolve and figure out where this background radiation is coming from, above or below, we need something higher than the Eiffel Tower. So he devised a set of electroscopes that would work in a hot air balloon. And he took a number of flights in 1911 and 1912 to try and determine, does the radiation level change with altitude? In 1911, he ascended in his hot air balloon and his little collection of electroscopes. He ascended to 1,000 meters. And even at that point, way above the height of the Eiffel Tower, it still wasn't quite clear what was going on. The radiation levels didn't seem to change drastically, and given they weren't necessarily super accurate, they couldn't really tell what was going on. But undeterred, he decided to continue with his experiments, and in 1912, he flew to 5,000 meters. Bam! Yes, the radiation levels increase dramatically when you go high enough. So yes, the ambiguity earlier was simply because you weren't going high enough away from the Earth. The radiation levels increased with height. That is totally inconsistent with the idea that the background radiation is coming from any radioactive rocks below our feet. So it's definitely coming from above, according to Hess's experiments. But still you have the question, okay, it's coming from above, but where? Is it coming from the sun? Is it possible that the sun, as well as being a source of heat and light, Is it possible that the sun is a source of radioactive particles raining down on Earth? How are you going to tell? Well, one option is you take your radiation detector up in a hot air balloon in the day and see what radiation levels you get at 5,000 meters, and then you do the same thing at night. But do you really want to fly a hot air balloon at night to a height of 5,000 meters in the dark, not knowing where you are, which way the wind is blowing, or where you're going to land? Correction, where you're going to crash, because you can't see where you're going. No one in their right mind would fly a hot air balloon at night. So how are you going to tell if it's coming from the sun or not? Hess had a brilliant idea. You fly your hot air balloon on the day of an eclipse. Fantastic. You take your radiation readings, you wait until the moon starts to cover the sun, and you see if the radiation levels go down or go up or stay the same. He concluded the sun is not a source of cosmic radiation. In other words, radiation is genuinely cosmic. It's not just the local cosmos, it is beyond the sun. Yes, the sun does produce some charged particles, but most of the background radiation that we're seeing are not coming from the sun, they're coming from somewhere else. And that's why Hess was awarded the Nobel Prize in Physics in 1936, effectively the discoverer of cosmic rays, by showing with these balloon flights that it was coming from above and it wasn't coming from the sun. This is the best idea that we have at the moment as to what's going on. Charged particles, cosmic ray particles, are slamming into the Earth's atmosphere and producing a cascade, an avalanche, if you will, of other particles coming down until they reach ground level. This particular little artist's impression here is not great for a couple of reasons. Mainly because it shows two showers going on at the same time, and that doesn't seem particularly likely. It is more likely that one particle hits and generates a shower, and then maybe later another particle hits and generates a shower. It's unlikely there'll be two at the same time. And it also implies that these showers seem to be coming from a very bright star, and it's fairly obvious what the source is. No, it's not obvious what the source is, but it's good enough to give us the impression that one particle coming in and hitting the top of the Earth's atmosphere produces an avalanche, because each individual particle coming in hits one of the atoms in the Earth's atmosphere, which produces more particles, which produces more, and then you get this avalanche effect. So this cartoon on the right gives you an idea of what's going on in a much simplified way. We talk about any particle that's hitting the top of the Earth's atmosphere, we call that a primary cosmic ray. We'll think about where they come from shortly. But if a particle comes in and hits something in the Earth's atmosphere, it produces this cascade of secondary particles, and they're called secondary cosmic rays, or secondary particles. Each of the particles that are generated share the energy of the incoming particle. So an incoming particle might be quite energetic, and then it might share its energy with two or three other particles, each of which share their energy with two or three other particles, and hence you get this avalanche effect. That means that if you were able to add up all of the energy of all of the particles that you can detect at ground level, you can work out what the energy of the incoming particle was in the first place. And this particular image here is not particularly good either compared to the last one, because it's not a question of one incoming particle generating a dozen secondary particles. It's much more likely that one energetic particle might generate thousands, or more likely millions, of secondary particles cascading their way through the atmosphere, arriving at ground level. What are these secondary particles? Well, there are quite a few possibilities. Some of them are stable, but quite a few of them are unstable. They are not the familiar building blocks of atoms that we are used to. In other words, protons, neutrons, and electrons. Some of these particles that are being generated by an incoming particle hitting the Earth's atmosphere, for instance, one of them is called a muon. This is nothing to do with the atoms that we're made of. A muon is a completely different fundamental particle. It's a sort of cousin of an electron. It's like a very heavy version of an electron, similar to an electron in terms of its properties, except that it's 200 times more massive. But these muons are being generated They have no part to play in atoms, but they seem to be quite important when it comes to cosmic rays. Muons are unstable. Remember, they're not part of what we're made of. A muon will only live for a few millionths of a second. So it might be generated in the upper atmosphere, and a few millionths of a second it might have come through a Geiger counter or a cloud chamber, but then probably its life is over. It will end up going through the cloud chamber, through the floor, into the Earth's crust. It might travel a few hundred meters, and then it ends its life. So muons only exist for a tiny, tiny fraction of a second, but it's still possible to detect them. There's one, for instance, again, a picture taken on my kitchen table. There's the familiar bottom of the cloud chamber, and that is the set of droplets that are left behind when a muon travels through the cloud chamber. We can tell that's a muon, not an electron, because it's a relatively straight line. It's an almost perfect straight line. Whereas an electron would be much more wiggly because an electron is much lighter and will get rattled around like a ball in a pinball machine. So the question is, okay, primaries come in, generate secondaries like muons and a whole load of other particles. So far we've thought about the secondaries and we've been measuring secondaries here at ground level, but what are the primary particles? Well, we can only actually answer that question by putting detectors up into space and finding out what those particles are. But we have been doing that for a few years now, and we now know what they are. Decades of research has told us that primary cosmic rays, most of them are protons. 90% of the particles coming in that are generating these showers on Earth, 90% of them are protons, the nuclei of hydrogen atoms. Approximately 9% are alpha particles, 2 protons, 2 neutrons. They are the nucleus of helium atoms. And all the remaining 1% or so are the nuclei of heavier atoms. Which atoms? Well, essentially all the atoms in the periodic table, roughly speaking, in the same sort of abundance as the abundance of materials, abundance of elements that we find in the Earth's crust. In other words, something in the universe is generating nuclei of atoms. It's like you're taking an atom, stripping all the electrons away, leaving yourself just the nucleus, and then accelerating them until they eventually rain down onto the surface of the Earth, onto the atmosphere of the Earth. So there's nothing unusual about the particles themselves. They're just the nuclei of familiar atoms. But we can still ask the question, well, what is it, though, that strips the electrons off and then sends these nuclei hurling in our direction? So we can ask ourselves how we go about detecting cosmic rays. How can we detect them? I've already shown you a couple of demonstrations. One is the Geiger-Müller detector, or the Geiger counter if you prefer. What is it that's going on inside the detector itself? Well, it's a relatively simple device. It's really just a tube filled with gas, an inert gas, and a high voltage electrode down the middle relative to the case. Any radiation that comes in will ionize the atoms in the gas inside the cylinder. In other words, strip the electrons away from the nucleus. Instead of a neutral atom, you'll end up with a positively charged nucleus, a negatively charged electron. Because you've got a high voltage, they will move towards the relevant electrode, and that ionization will result in a current. And that current, the yellow box, effectively converts into a click. So in other words, whenever we see a current, that indicates that something has ionized some of the atoms inside, and therefore a particle has passed through the detector. And that's all you get, a click saying something has happened. So you don't really get any indication of what it is that's passed through. The cloud chamber is a little different. How did the idea of the cloud chamber start? Well, it started with Charles Wilson, who in 1894, it is said, was on the top of Ben Nevis and saw a Brocken spectre. I'm not sure if any of you have seen that. If you look with the sun behind you, you cast a shadow. In the right conditions, if it's a very misty day, if there's a little cloud cover at the top of the mountain and the sun is behind your head, you get a shadow cast and you get various optical phenomena. You get various colors appearing like a halo around the shadow of your head, so-called Brocken spectre. Charles Wilson said, "This is interesting. I wonder if I can study this, but I really don't want to keep taking my equipment to the top of Ben Nevis. This is not the good way of doing science. Let's see if I can reproduce this in a laboratory. Instead of taking my equipment to the top of Ben Nevis, can I actually generate a cloud in my laboratory? In other words, can I put a cloud in a jar?" So that's what he wanted to do. He perfected in 1911 the first cloud chamber. He basically took a whole load of water vapor, expanded it very quickly so that the water was just at the point of condensing, so that he could study the phenomena of how does light interact, how do we get these colored halos around shadows. That's what his interest was, but he kept finding that whenever he was trying to do his experiments, he kept finding contrails through his cloud chamber. He realized that charged particles passing through his cloud chamber were leaving tracks of water droplets, effectively clouds in his cloud chamber. So he got water droplets condensing to form tracks. This he found rather annoying because that's not what he wanted, but the particle physicists of the time said, "This is fantastic. We now have a detector that allows us to see the passage of charged particles." So instead of just working out, well, I think this is what's happening, they can actually see what's happening. They can use cloud chambers to say, well, there's definitely a particle traveling this way, there's definitely a particle traveling that way. I'm going to do an experiment. I'm going to see what particles come out of this radioactive sample. They will bend in a magnetic field one way if they're charged positive. They'll bend in a magnetic field the other way if they're charged negative. You can tell all sorts of things about the particles if you look at how they behave in a cloud chamber. So this revolutionized particle physics for quite a few decades. In 1927, Wilson was awarded the Nobel Prize in Physics for, quote, "the most original and wonderful instrument in scientific history." That is quite an accolade from anybody to say that the cloud chamber has transformed physics in such a way that this is one of the most important, if not the most important, instrument in scientific history. Plenty of people will argue there are plenty of other instruments as important, but that showed you what difference it made at the time. So Wilson's cloud chamber in 1911 has morphed somewhat in that I've made a slightly different version of it sitting here on the front bench. It's using a little new technology that wasn't available to Wilson, and it uses alcohol rather than water because that happens to be easier. It's still the basic same idea. It's a cloud in a jar. It's a jar, and in order to make a cloud, we put in some agent, in this case alcohol, IPA, isopropyl alcohol. The alcohol is put in the top and warmed up to generate alcohol vapor, and the bottom is kept cold. And if you generate vapor and keep the bottom cold, you'll generate clouds, and when the clouds are just about to form, it'll be possible to see the contrails, if you like, the condensation trails of any particles that are passing through the cloud chamber, as we've been seeing earlier this evening. So I'm not going to go into detail, but basically all of the components of this cloud chamber, I essentially bought all of them from Amazon. It's a mug warming coaster on the top there, the sort that you keep your tea warm with. Plug into the USB, keeps your tea warm. I've used that upside down to get the top warm, and the bottom is a little refrigeration unit which you can buy on Amazon for about £15. So if you want to build yourself a cloud chamber, I brought along instructions for how you can do one yourself. It'll cost you about £35, assuming you haven't got all the bits already lying around in your kitchen and or garage. If you have to go and buy all the bits, it'll cost you about 35 quid if you want to see subatomic particles for yourself. So let's just see if it's behaving itself. I've taken the radioactive sample out, so it might now have sorted itself out, and we might get back to, there we go. There was a little muon coming through there on the right-hand side. I'm not going to waffle for too long, but let's just see in the next few seconds. There's another one coming through at the bottom. We should be seeing some signs of a cosmic, another one coming through, another one there. That looked like a muon to me. A number of particles will be going through the cloud chamber, approximately one every second. Some of them will be very unspectacular if they happen to be coming through vertically. The longest tracks indicate something that's actually coming through sideways. Okay, there's definitely still a few there, so the cloud chamber is still working. So, okay, fine. take a closer look later if you so wish. So again, this is a video I prepared earlier, just in case it wasn't working too well. Lots of individual bits there. We've got that very bright one on the right-hand side was a proton, I think, and there's lots of other tracks coming through every once in a while there. Again, just in case it wasn't working, I took a fairly long video of the cloud chamber in action when it was sitting on my kitchen table, and then I added up all of the individual frames whenever I saw a track of a particle to give you an idea, a montage, if you like, of all the particles that came through over the course of maybe an hour or so. And that gives you an idea of what's actually coming through. It's very difficult to see what's what because all of the tracks are on top of each other compared to just getting one at a time. But what you can see is that there are maybe half a dozen or more very bright, sometimes short, but definitely straight tracks. Those are probably protons. Anything else you can see in there that looks a little fainter but still straight is a muon. Anything in there looks decidedly wiggly, that must be a very lightweight particle, so that's an electron. So with a bit of practice, you can start to actually tell what's what. What I haven't shown on this particular graphic, this particular image, is any alphas, because alphas are not cosmic. Alphas that you do see in a cloud chamber can't be coming from the cosmos because alphas cannot travel through glass. Glass is just too thick for them to travel through. And so any alphas that we do see in a cloud chamber must be coming from atoms that are inside the cloud chamber, in other words, radon. So yes, we do see alphas in cloud chambers, but they are radon, not cosmic rays. So these are the cosmic rays: muons, electrons, protons, probably not much else. That probably accounts for most of what we see. Experiments are being done not just by amateurs like me who play around in their kitchen, but there are a number of different experiments looking for cosmic rays and have been doing for many, many decades. For instance, the Voyager spacecraft that were launched in the 1970s and the flying out of the solar system, they have cosmic ray detectors on them. I believe the cosmic ray detectors have just been switched off, which is a bit of a shame because they've been working diligently for the last 50 years. Amazing. Voyager 1, back in 2012, measured a significant jump in the readings it was getting of cosmic rays, indicating that it had left the solar system and was now traveling through interstellar space. And the same happened to Voyager 2, but it happened in 2018 because Voyager 2 is traveling somewhat more slowly. Voyager 1, if you remember, went to Jupiter and Saturn. Voyager 2 went to Jupiter, Saturn, Uranus, and Neptune. When Voyager 2 went past Neptune, it didn't use a gravity assist to accelerate, it used a gravity assist to slow down because it wanted to go and see Triton, its moon. So Voyager 2 actually slowed down when it went past the last planet in its series, and so Voyager 2 is leaving the solar system rather more slowly, so it took a few more years until it noticed the cosmic ray flux changed, indicating that it has left the solar system and is now flying through interstellar space. There are cosmic ray experiments elsewhere. For instance, there's a cosmic ray experiment sitting on the International Space Station. There it is circled in red. And just to give you an idea of scale, there's an astronaut. I don't think the astronaut is fixing it. That just gives you an idea of scale. This particular detector is sitting on the ISS, and therefore it's effectively measuring what is arriving at the atmosphere of the Earth. So unlike the experiments on the table in front of us here saying what's happening at effectively sea level, experiments on the ISS are telling us what are the primary particles that are arriving at the top of the atmosphere. There are some rather big experiments to try and measure the secondaries. It's cheaper to measure secondaries because you can have the experiments at ground level. It's quite expensive to put any experiment into space. So a lot of effort is being put into measuring secondaries. The shower that's produced by some particle entering the atmosphere, if you have enough detectors, you can spread them over a large area because these showers can spread over many, many, many square kilometers. So for instance, there's an observatory called the Pierre Auger Observatory in Argentina where they have a number of these detectors. I'll say what the detectors are in just a moment. But in order to try and catch as many of these secondaries as possible, they've spread these detectors over a large area. And when I say a large area, I mean the area the size of Luxembourg. Okay, so this is a big observatory. It's the size of a country. Okay, a small country. What are the individual detectors? They're not cloud chambers, because they don't want to have to photograph tracks and then figure out what the hell's going on in there. These are detectors that are effectively water tanks. And what they're looking for is particles that pass through the water tank producing a flash of light. And we can ask ourselves, okay, but why does a particle moving at some speed through a water tank produce a flash of light? Well, it's analogous to the idea of what happens when a fast jet flies through the air. If the aircraft is traveling faster than sound, what happens? If the aircraft is traveling faster than sound can travel through the air, it generates a shock wave, a sonic boom, if you prefer. And the same is true if a particle travels through water faster than light can travel through water. Now, we know that nothing can travel faster than light through a vacuum, but it is possible for a particle to travel through water faster than light can travel through water, because light gets slowed down. The same is also true of the air. So the analogous sonic boom in light, if you like a photonic boom, is something that people are looking for to see what particles are arriving down here in the Earth's atmosphere. So here's a little video saying you've got an incident particle coming in. It produces a cascade of secondary particles, but if these particles are moving fast enough, they produce the equivalent of a photonic boom, a flash of blue light. It's called Cherenkov light or Cherenkov radiation, if you prefer. And if particles are going fast enough, they will produce this flash of blue light. And I mean a flash, a billionth of a second or thereabouts. So telescopes are looking for this blue flash in the atmosphere. The Cherenkov telescope array, some of which is in the Atacama Desert and some of which is on the island of La Palma in the Canary Islands. A whole set of telescopes are looking into the sky to see if they can see this blue flash, indicating that very energetic particles are traveling through the atmosphere of the Earth. The same principle applies to those detectors I was just showing you from the Pierre Auger Observatory. If any particle travels through the water, going faster than light can travel through the water, again, there's a blue flash which is then picked up. It doesn't matter whether it's air or water, as long as the particles can travel fast enough. And in fact, it doesn't really matter if the water is frozen. So these telescopes are looking into the sky, but it's also possible to build yourself an observatory in the Antarctic. There's the Ice Cube Observatory, and underneath the ice of the Antarctic Observatory, there's the ice going all the way down to the bedrock. Eventually you do get to bedrock if you go through the ice of the Antarctic cap. The scale here is a little difficult, so let me just point out that that's the Empire State Building on the left-hand side. So this is 2 kilometers of ice. That's how thick the ice cap is at the South Pole. What they have done is drill down and put loads of photodetectors in a sort of string of pearls arrangement, and they've instrumented a huge cube of ice, 1 kilometer by 1 kilometer by 1 kilometer. So it's basically an ice cube 1 kilometer cubed. And all of these photodetectors, thousands of them, are looking for this characteristic blue flash. If a particle travels through this cube of ice faster than light can travel through the ice, then you get a blue flash. So this is a little animation of what they might see. If a particle is going fast enough, it'll generate a blue flash, and then these photodetectors will pick up the blue flash. And if you look at which photodetectors have fired, then you can work out where this particle came from, just from geometry and tracing back through the pattern of which photodetectors have fired. So in principle, you can tell where these particles are coming from, which leads us to this last section. Okay, we can see secondary particles at ground level. They're coming because primary particles are hitting the Earth's atmosphere. Where are those primary particles actually coming from? Well, a little aside. Remember that it's just over 100 years, give or take a few months, since Hubble said these spiral nebula that we see in our galaxy are not in our galaxy. They are actually galaxies in their own right. In November 1924, the great debate was settled by determining, for instance, that the Andromeda galaxy is actually 2 million light years away. It is not a nebula inside our own galaxy. So you could argue that the question that we were raising before, cosmic rays, if they don't come from the sun, where do they come from? Milky Way or something else? Well, because of Hubble's argument that we now know that the universe contains billions, if not trillions, of other galaxies other than our own Milky Way, the real question is, well, are the sources of cosmic rays from the Milky Way, in other words, are they galactic, or are the sources of these particles hitting the Earth's atmosphere extragalactic? And the answer is, well, okay, do we know what mechanism could actually produce energetic particles? Well, theorists have said, well, surely energetic events are likely to produce energetic particles that could be raining down on the Earth. For instance, supernovas produce shock waves, and could those shock waves accelerate particles and strip the electrons off and send the nuclei humming across the galaxy? And also, is it not possible that supermassive black holes, which we think are at the center of every big galaxy, if not every galaxy, supermassive black holes often have jets coming out, and those jets perhaps could accelerate particles and send them our direction. So we're not too sure of the mechanism. Theorists say, well, yeah, maybe shock waves can accelerate particles to very high energies, but the mechanism is still, well, the jury is out on that. Is it a question of the shock wave has to continually accelerate the particle? Because some of these particles that we're talking about are very, very high energies that we think are hitting the top of the Earth's atmosphere. So you might say, surely this is an easy problem. Why haven't we figured it out already? All you need to do is to use these various observatories that I've been talking about to say, well, we've got a shower of particles here. We know the geometry. Either these have gone through the South Pole or these have gone through the observatory in Argentina. We've seen this shower. We know the geometry, so we can simply trace it back and see where that thing came from. In other words, trace these lines back, and there you've got your culprit, the smoking gun, the source. Isn't it easy? Simples? No, and it isn't easy for a number of different reasons, but mainly because charged particles, whether they be positively or negatively charged, are deflected by magnetic fields. And magnetic fields are pretty much everywhere. We have a magnetic field around the Earth. Maybe that's not so much of a problem because, well, we know charged particles from the sun, for instance, will end up spiraling around these magnetic fields, and that's why we end up getting particles funneled into the north and south poles, and we get aurora every once in a while. But it's more of a problem to realize that magnetic fields are not just local to the Earth. Magnetic fields are everywhere out there. So here on Earth, we know from our school days that if we want to see what a magnetic field looks like, all we do is sprinkle iron filings on it, and then we can see where the magnetic fields are, and we can get an idea of how strong they are. How do we do that inside the Milky Way? Well, it's sort of possible because dust particles act a little bit like iron filings. If we can work out which way dust particles are aligned, because dust particles are very rarely spherical, they're usually slightly elongated, so they will tend to line themselves up in magnetic fields. And Planck has already looked at the polarization of light and figured out that this is where we think the magnetic field of the Milky Way is going. But it's a rather complex beast. Trying to figure out how would a charged particle bend in a magnetic field that's as complex as that, well, that would be tricky. And we, at the moment, haven't got a chance of working out where the magnetic fields might be in intergalactic space. If these things are coming from outside our galaxy, they are having to navigate the magnetic fields outside the galaxy, and we don't know how to measure the magnetic fields out there. So one solution is to say, well, let's not worry about the magnetic field. We know from our physics, our school book physics, we know that really energetic particles don't care much about magnetic fields. Slow-moving particles will be deflected by magnetic fields, but if they're going fast enough, they will go in almost a straight line. So let's not worry about where the magnetic fields are. Let's concentrate our search for looking at the most energetic cosmic ray particles, and then hopefully we'll be able to pin them down as to where they're coming from. So what do we mean by energetic? Well, the energy of a photon of visible light, in other words, the energy of the photons hitting my hand in front of the screen here, let's call that a unit of 1 eV. We won't worry about what eV actually means, it's just the unit we're going to use. So normal visible light has an energy of 1 eV. 1,000 times higher, and we would have the energy of an X-ray, which of course are rather more penetrating. 1,000 times more again, and we have the sort of energy that might be an alpha or a beta or a gamma ray coming out of a radioactive material. Cosmic rays are off the scale on this sort of thing, thousands, millions, billions, trillions of times more than the sort of energy that we're talking about with visible photons or X-rays. So cosmic rays go all the way from much more energetic than the sort of particles we've been looking at in radioactive decay, up to trillions of times more than that. And just to give you a sense of scale, the Large Hadron Collider is sending protons around with this sort of energy, indicated by the left-hand arrow here. And if they ever get around to building themselves an even more energetic accelerator, it'll be roughly where the right-hand arrow is. So the most energetic cosmic rays are way, 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 way more energetic than the sort of particles that we can generate in particle accelerators in CERN. As a rough indication of how many we can expect, the flux, as a function of energy, the left-hand band there in yellow, that we think the lowest energy cosmic rays are probably coming from the sun. The middle ones here, the middle energies, we think are coming from the galaxy, and the most energetic ones on the right-hand side, this sort of purpley color, we think are extragalactic. A lot of that is supposition, but we still need to do more research. But if we look at how many particles we expect to get, we get a lot of the low energy ones and very few of the high energy ones. At the low energy, we might get one for every square meter of the Earth's surface arriving. So that's quite a lot. But in the middle ground, we might only get one per square meter per year rather than per second. And if we are interested in the most energetic cosmic rays, it might only be one per square kilometer per year. So these are the really interesting ones. How can they be so energetic that they get that much energy? But these are precisely the ones that we think will be independent of any magnetic fields. So there's a lot of interest in these so-called ultra-high energy cosmic rays. And a few of them have been discovered. One of them, this one, was the second most energetic particle ever detected hitting the Earth. It hit the Earth. This is, of course, an artist's impression of what that might have looked like. So there was a telescope array called the Telescope Array Utah, USA. A number of different detectors at ground level picked up part of the shower. And if you can detect a whole load down here, you can figure out what must the energy of the incoming particle have been in order to give us this many hits, this many particles arriving at ground level. This was Astronomy Picture of the Day back in 2023, and it was talking about the analysis of data that was taken in 2021. This is the so-called Amaterasu event. Amaterasu is a Japanese god. It means something like shining from heaven, which is a wonderful translation. But Amaterasu should not be confused with tiramisu, which is a completely different thing, and I presume that's what they started eating after they saw this particular event. So they had this particular event. They thought, fantastic, this is really energetic, and therefore we should be able to do what we want and trace this back. So if it's true that energetic particles are not deflected much by magnetic fields, regardless of how big those magnetic fields are, then we're onto something. Let's trace the direction of the Amaterasu event back to its source. And this is what they did a couple of years ago. And they found that the direction points to, pause for dramatic effect, nothing. There was no obvious candidate. There was no supernova remnant in that position. There was no galaxy with a supermassive black hole that looked like it could be the candidate for producing the Amaterasu event. So this means one of two things. Either the source of cosmic rays is not supermassive black holes or supernova, or those are the sources, but the particles are getting deflected more than we thought. Maybe the magnetic fields out there are much stronger than we appreciated, and even these really energetic particles are getting deflected a bit, so that when we think it came from over there, it actually came from over there. Okay. No supernova, no supermassive black hole at the moment are the smoking gun for the sources of cosmic rays. So absolutely, we need to take more data, and maybe if we have 100 times as much data, we'll start to get a picture of where are these cosmic rays actually coming from. Just to give you an idea of how energetic these particles are, Amaterasu was the second most energetic event seen. There was one that was more energetic than that by a factor of, I think, about 2 or 3 times as much. Physicists think about energy in the same way we think about speed. How close to the speed of light corresponds to how energetic. The more energetic, you're never going to exceed the speed of light in a vacuum, but the closer you can get your particle to the speed of light, the more energetic it is. So if you calculate how energetic the particle is, you can say, well, okay, let's calculate how close to the speed of light must it have been traveling in order to have that much energy. The Amaterasu was number 2. The most energetic particle ever seen was the oh my God particle, because when the scientists first saw it and calculated how much energy it had, they literally could not believe that a single particle, whether it be a proton or an alpha particle or the nucleus of an atom, how can one particle possibly have that much energy? And it is still a bit of a mystery. So I'm just going to show you here how fast it was traveling. Take the energy, recalculate it as how fast was it traveling as a percentage of the speed of light. The oh my God particle was calculated to be traveling at 99.9999999. 999. We're not done yet. 999. Still not done yet. 999. 999. Don't worry, we're nearly there. 995% of the speed of light. 99 point ridiculous number of nines. What can possibly accelerate a particle, a proton, or something else to that incredible speed in order that it has that much energy when it slams into the Earth's atmosphere and produces the shower that was seen either for the oh my God particle or the Amaterasu particle? One way of visualizing just how fast this particle is, because we can all count nines, but it's very difficult to figure out what that actually means. Let's just have a hypothetical race. Let's imagine we have a race over a complete vacuum over 100,000 light years, so something about the size, a racetrack about the size of the galaxy. Let's imagine a race between a photon of light and the cosmic ray particle that we've just been talking about. They both start from the start line at exactly the same time. Now, of course, light is going to win because nothing can go faster than light, and the cosmic ray is going a little bit slower than that. But you can ask yourself, if the racetrack is 100,000 light years long, and they both start at the same time, when light crosses the finishing line, how far behind it is the cosmic ray? And the answer is, after 100,000 light years, the cosmic ray has lost the amount of ground equal to 5 millimeters. In other words, if you had a stopwatch and you said, let's time how long they take, it's going to take, obviously, 100,000 years for light to travel that distance. If you start the stopwatch when light crosses the finishing line, and you stop the stopwatch when the cosmic ray crosses the finishing line, those two times will be only a few picoseconds apart, much, much less than a nanosecond. So how can anything be going that fast? What mechanism could possibly accelerate a charged particle up to those sorts of speeds? And that's where we're going to have to leave it, because it is still a mystery. We know that cosmic ray particles are accelerated somewhere, somehow. We don't know where, and we don't know how. It is still an active area of research. Maybe supernova and supermassive black holes are sources. it seems quite likely because they are the most energetic things we can think of. Of all the things we've seen in our galaxy and all the other galaxies that the Hubble and the James Webb and all these other telescopes have been looking at, the most energetic events appear to be supernova and the jets produced by supermassive black holes. So surely they must have a role to play. But at the moment, we can't pin that down. Maybe we're overlooking something. Maybe there's some other way of accelerating particles which we have missed. We know cosmic rays are deflected by magnetic fields because they are charged particles. We think that low energy particles will be deflected a lot and they'll get their paths absolutely scrambled. We're hoping that the most energetic ones will travel in something close to straight lines. Some particles make it past Earth's magnetic field and hit the atmosphere, which then creates an air shower of secondary particles. Some of the secondary particles make it to sea level, and we know some of those particles, like muons, electrons, protons, we've seen those in cloud chambers, and they make clicks in Geiger counters. So when you listen to the clicks in a Geiger counter, when there's no radioactive samples close to it, or when you look at tracks in a cloud chamber, you're effectively, in the case of the Geiger counter, listening to particles that could have started their journey in a supernova in our galaxy, or possibly close to a black hole in another galaxy entirely. So in a sense, you're listening to the cosmos. Thank you for listening.